Hello friends, welcome to my channel. So it is chapter number 22 and it is about conjugate addition and nucleophilic substitution reaction in aromatic compounds. So first we will try to find out how we can recognize that a nucleophile will show a conjugate addition or it will show a direct addition of carbonyl group of alpha beta unsaturated compounds. So we have seen in previous chapters that double bonds are nucleophilic in nature. They will show electrophilic addition reactions. But if you have a double bond in conjugation of carbonyl compounds like this, they can show electrophilic characters. Right? Next question comes that nucleophile can attack on this double bond or it can, and then it will show conjugate addition. And second possibility is that it can show direct attack on this carbonyl compound. Okay, so we have two possibilities. Then this question comes that how we can recognize that a nucleophile will show you conjugate addition or it will show direct addition. So we have certain factors which can help us to determine their role. So first thing is role of temperature. For example, if you have a alpha beta unsaturated carbonyl and then you are using NaCN. Right, so we know that CN can show direct addition of this carbonyl to form your nitrile compounds. Right, second possibility is it can attack this nitrile group, can attack on this carbon, then this double bond will shift here and then this will shift here. This is your conjugate addition. Right, so if you have low temperature conditions, then direct addition will show you the final product, means the reaction will be like this. This is direct addition. So I can write down here DA for direct addition. And if you are using high temperature conditions, then it will show conjugate addition, means CN will attack on this carbon, then this bond will shift here. So you will get a product like this, right? This will be the product. So this product is known as kinetic product. At low temperature condition, kinetic product will form. And under high temperature conditions, thermodynamic products will form. So thermodynamic products are more stable as compared to kinetic product. We know that kinetic products are the products which are formed at faster rate, while thermodynamic products are formed at slow rate, and these reactions are irreversible in nature, while the formation of kinetic product is highly reversible reaction. Then question comes, why direct addition is faster in nature? Because if you look at this alpha beta unsaturated compound, nucleophiles attacks on electrophilic center. So this carbon has some positive charge and this carbon also has some positive charge. So they are electrophilic in nature. But at this center, at this carbon center, due to the presence of this oxygen, its positive charge is slightly higher. It is more electrophilic in nature. So this nucleophile attacks readily on this carbonyl compounds rather than this one. So that is why your kinetic products are faster in nature. Formation of kinetic product is a faster reaction and formation of thermodynamic products is a slow process. Then why conjugate addition product is more stable? This one is thermodynamic products are more stable in nature. So what is the reason behind it? So if you see at this, look at this kinetic product, here we are forming a new sigma bond. This new sigma bond is formed, and here we are forming a new sigma bond by breaking the 1 pi bond. This carbonyl bond is break and then it will form a new sigma bond. So this carbonyl bond has energy of equal to 369 kilojoule per mole. While if you are forming thermodynamic product, then in this case this carbonyl bond will remain as such. Here we have a new sigma bond and we have a sigma bond and there is breakage of carbon double bond carbon and it has energy equal to 280 kilojoule per mole, right? So we need a small amount of energy to break this bond, while we need a higher amount of energy to break carbonyl bond. That is why this product is more stable as compared to this direct addition product. Factor affecting is structural factor. The next factor is structural factor. So more reactive carbonyl compounds will show direct addition product, right? So if you have suppose a alpha beta unsaturated compound containing carbonyl acyl chloride group, it has much higher reactivity as compared to enols than enones. So this reactivity order can be compared by using the acid subderivatives. We have seen in the chapter on acid derivatives that acid chlorides have much higher reactivity than aldehydes, than ketones, and then with esters, and last for amides. So similar order will be followed here, right? So if you have, for example, in this case we have enols and we are using butyl lithium, so this butyl lithium will show direct addition product. So we will get, it will form OH after hydrolysis, and this butyl group will attach on this carbon directly. At the same time, if you are using the same reagents and your carbonyl compound contains amide group, then it will show conjugate addition, means butyl group will attack on this carbon, this bond will shift here, this will shift here, and when it will come back, it will show protonation at this carbon, right? This will be your final product. Next example is if we are using ammonia and we are using here acyl chloride, it is very reactive, so it will show direct addition. So this Cl group will be replaced, it will act as a leaving group when this carbonyl group will come back, and NH2 will attach here. And then we are using when NaBH4 and we have a aldehyde group here, it is enol, right? So enol are very reactive, so it will show direct addition. Now you don't need to remember that in case of alpha beta unsaturated aldehydes, NaBH4 will not attack on double bond, while it can attack on double bond of alpha beta unsaturated carbonyls. Now you can easily find out it that any nucleophile will show direct addition on more reactive carbonyl compounds, and it will show conjugate addition with less reactive carbonyl compounds. So in this case, this double bond will remain unaffected and it will directly attach with this carbonyl group, will do its reduction. At the same time, we have alpha beta unsaturated carbonyl, so it is less reactive as compared to enol. That is why it will show conjugate addition and you will get a product like this. In next example, we have a alpha beta unsaturated ester. So ester group is less reactive, so this NaBH4 will show conjugate addition, but you have to also remember that NaBH4 cannot reduce esters, it can reduce only carbonyl, it can only reduce ketones and aldehydes, so ester will remain unaffected. You will get this product. Next is conjugate addition with copper 1 salt. So if we are using a Grignard reagent with alpha beta unsaturated compound, this Grignard reagent will act as a strong nucleophile, hard nucleophile, right? So it will show direct addition. We know that we have already discussed that in case of carbonyl compounds, this carbon center is hard electrophile in nature, right? And the double bond is soft electrophile and the double bond of alpha beta unsaturated compound is soft electrophile. So if we have a Grignard reagent, then it will provide me hard nucleophile, so it will show direct addition. So this will be the product. One more possibility is it will show elimination reaction and give me this product also. But if we are using cuprous chloride 0.01% equivalent with Grignard reagent, then it will combine with this Me- to form methyl cuprate. So it will act as a soft nucleophile, and this soft nucleophile will actively attack on this double bond, and then it will show conjugate addition. So the reaction will be like this. We can also write down it like this is enol form. We can also write down in ketonic form. It will also give this elimination product, but its percentage is lower. So this is 83% in this case, and this product is 7% only. And in first case, this compound is 43%, while the elimination product is nearly 48%. Other groups can also do conjugate addition. So in case of nitrile group, we can see this thing in alpha beta unsaturated compound containing nitrile groups and nitro groups. And we are using here diethylamine, so it will show conjugate addition. right? Then this charge will come back and it will show protonation at this carbon, right? Similarly, in this case, we have nitro group here and we are using NaBH4, so it will show conjugate addition. So this double bond is reduced and this NO2 group will remain as such. So till now we have seen conjugated addition reactions. Now we will take some conjugate substitution reaction. For these reactions, we will need some leaving group, some good leaving group present on double bond. The next thing is it will give me preferentially E alkene, right? So this MEOH will attack on this double bond. Okay, so this is not acyl chloride, so don't confuse with that. It has only Cl group attached at double bond. Okay, so it will show conjugate addition, it will not show direct addition. Then this bond will shift here and it will shift with on this oxygen. So we have this one as intermediate. Then this charge will come back, it will shift here and this Cl will be removed. So this will be the final product in which this Cl group is substituted with this methoxy group. So it is a substitution reaction, not the addition reaction. This double bond will remain as such, right? And this double bond is E alkene. Okay, so preferentially E alkenes are formed. So for such type of reactions, for conjugated substitution reaction, we need some leaving group at double bond. Then we will take nucleophilic epoxidation. So we have seen epoxidation with the help of MCPBA, and MCPBA is electrophilic in nature. So they attacks on electron rich alkenes, right? But if we are using H2O2, it will act as nucleophile, right? It will also cause epoxidation, but it will act as a nucleophile and its nucleophilic character is better than OH minus. While it is better because we have two oxygen atoms and the electron, lone pair of electron present on these two electron oxygen atom will raise the energy of HOMO. Okay, and we know that if a nucleophile has higher energy HOMO, it will act as a better nucleophile. It can show good HOMO LVMO interaction, so that is why it is a better nucleophile. But it is a weak base. It is weaker base as compared to OH. Why it is weaker base? Because we have one oxygen atom next to this O minus. So this will show electron withdrawing effect. It has higher electronegativity, so it will pull electron density towards it, right? So it will act as a weaker base as compared to OH minus, but its nucleophilic character is better than OH minus, right? So it will act as a soft nucleophile. Soft nucleophile means it will attack on carbon double bond carbon of carbonyl alpha beta unsaturated compound. But if we are using OH minus, then it will attack on carbonyl group because it will act as a hard nucleophile and its interaction will be due to electrostatic interaction. We have already discussed in previous chapters, when we have hard nucleophile, their interaction with electrophilic center is due to electrophilic interactions, while for soft nucleophiles and soft electrophiles, their interaction is due to HOMO LVMO gaps, right? So it will act as a soft nucleophile and will attack on this carbon double bond carbon of a alpha beta unsaturated compound. For example, if we have this carbonyl compound, then this HOO minus will attack on this carbon. This bond will shift. It will shift like this. Then this charge will come back and this will shift here and it will attack on this oxygen atom and this OH minus will be removed. So it will give me this product. So it is a very important point that MCPBA will attack on electron rich alkenes because they are electrophilic in nature, and H2O2 is nucleophilic in nature. That is why it attacks on electron deficient alkenes which are poor in electron density, like alpha beta unsaturated carbonyls. Okay, so this is the basic difference between the epoxidation of H2O2 and MCPBA. Next important point is, if I am using a double bond like this, if I am using MCPBA, it will show reaction in single step, right? So it will give me stereo specific product. Okay, but if I am using H2O2, then this reaction is not in a single step. This is not in single step. So there is free rotation about bonds, and that is why it can form more stable epoxides, trans epoxides, right? So it can give me a product like this in which these two groups on opposite side, so it will preferentially gives trans epoxides, while in case of MCPBA these two will remain on the same side. So these two are very important point about epoxidations. Then we will take nucleophilic aromatic substitution. So till now we have seen electrophilic aromatic substitution reactions. Aromatic ring or all the aromatic compound preferentially shows electrophilic substitution reactions, but they can also show nucleophilic substitution reaction. So which type of nucleophilic substitution reactions can be possible? If they can show suppose SN2 type reaction. So for SN2 type reaction, a nucleophile should attack from the inner side of this ring like this. So this is not possible. So they cannot show SN2 reaction. And if we are talking about SN1 reaction, then they should form a carbocation like this, right? And this lobe is your empty sp2 lobe. This is not p orbital like other carbocations. It is a empty sp2 orbital, and this is outside the ring. So it is highly unstable in nature. But due to this formation, this aryl cation, they can show SN1 reaction to some extent. So for nucleophilic aromatic substitution, our aromatic compound should have these three characteristics. First is an oxygen, nitrogen and nitrile containing group should be nucleophile in nature. A nucleophile should have oxygen, nitrogen, or it can have a nitrile group. Then second point is a halide group should be present, and then it will act as a leaving group, right? So we need a halide group also. Then third point is a carbonyl nitrocyanide group at ortho and para position of a leaving group. Okay, so these three things are very important. So we will discuss about these 2 points in following examples. So first we have chlorobenzene, and first we are doing its nitration, then we are treating it with hydrazine. So when we are doing its nitration, we can have ortho and para substituted products. So suppose we are doing nitration in excess of HNO3 and H2SO4. So what we will get? We will get NO2 group attached at ortho and para position. Okay, so in this case we have first requirement, that is a nucleophile should contain oxygen, nitrogen or cyanide containing group. So we have hydrazine, it has nitrogen as a nucleophile, it will provide lone pair of electron and can attack on this carbon, right? Then this carbon contains a halide as a leaving group, it has a halide as a leaving group. A carbonyl nitrocyanide group should be present at ortho and para position. So we have a nitro group present at ortho and para position. At both positions we have NO2 group. So how we can do this reaction? So I can write down this nitro group like this. So first step is this hydrazine will attack on this carbon. This bond will shift, this will shift here and this will shift here, right? So we will get, okay, then this charge will come back to its position and this leaving group will be removed. So we will get a product as this one will be final product. So similar type of conjugation can be possible if we have a group like this, nitro, carbonyl and cyanide group at ortho position. Then similar type of conjugation is also possible. Similarly, here we have one more example. So we have nitrogen containing group as a nucleophile. So it can attack on this carbon and this F halide will act as leaving group, and we have a group at para position which can help in conjugation, right? So we will get this one as final product. So we are using here K2CO3, a base which can help us in removal of this proton. When it will attach on this carbon, then it will form a structure like this, and then we are using a base which will remove this proton. Next type of aromatic nucleophilic substitution reactions are possible with diazonium compounds. So suppose I have a aromatic compound containing a alkyl group here. Then first I have to substitute it with nitro group. So it will attach at para position suppose. Then I can reduce it to amine using suppose hydrogen in palladium carbon. So this nitro group is converted into amine. Then I can convert this NH2 into diazonium compound using NaNO2 and HCl. this reaction take place at low temperature. So it will form diazonium compound. Then we can treat the diazonium compound in different substituents using various reagents. Suppose I am using Ki, then this N2Cl will be removed and we have a carbocation generated here. This is aryl cation, and then on which this Ki can attack and can form iodo substituted product. Right. Similarly, we can use H2O, so it will give me phenol. And if we are using CuX, where X can be Cl, Br, CN group, right, then it will give me X substituted here. So this type of compounds can also be possible. Then last aromatic nucleophilic substitution reaction is through Benzine mechanism. It will involve formation of an intermediate known as benzine. So suppose I have a bromobenzene and I want to replace this Br group with OH. So I can use any OH, and this reaction condition require very high temperature. We need to fuse it. Then it will give me phenol. But we can do similar type of reactions at low temperature also. Suppose I am treating this bromobenzene with a strong base like NaNH2 in ammonia. So this base will first remove a proton from this position. So this NH2 minus will remove this proton first. It is removed from the ortho position. This elimination leads to the formation of a negative charge here. Right? Then we have Br at ortho position, so it can pull this electron density towards it and it will form a new pi bond here. This new pi bond is abnormal and highly unstable because it is outside the ring. So because of its instability, they are highly reactive in nature. So on which this NH2 can attack, then it will take a proton from ammonia and it will form aniline. So we will take some more example based on this benzine intermediate. Right, so first step is this NH2 minus will remove a proton from this position and it will form benzine. So I am directly writing here formation of benzine like this. Now this NH2 minus can attack on this side of this carbon or it can attack on this one. Suppose I am attacking it on meta position first. So when I will attach it on meta position, then negative charge will be generated here and we have NH2 group attached here. Then this negative charge will take a proton from ammonia to form final product. The next possibility is this NH2 group will attack on this carbon. So it will give me, this is first possibility, and it will give me this product NH2 substituted at meta position, and in second possibility this NH2 will attach at ortho position. So when it is attached at ortho position, it can show clash with this OMe group and clash, or you can say it will show steric hindrance, right? Second thing is this negative charge is not stable in nature. This one is stable because we have oxygen of this methoxy, which is electronegative, and pull electron density towards it and stabilize this carbanion. While in this case, this negative charge is not stabilized, right? So the major product will be this one, meta substituted NH2 is major product, right? If I have suppose alkyl substituted bromobenzene, then it will give me a benzine like this, suppose, right? So this R is much far from this benzine, this triple bond. So we can have two type of product. It can give me meta product as well as ortho product. So there is 50-50 chance of their formation. Next thing is, suppose I have a electron repelling anion here, like I have OH at this position. Instead of R, we have OH here. So when we will use a base, this base will remove this Br as well as this proton. So it will generate a anion here, right? So if we place a negative charge at this position, suppose after shifting of this bond, and we have negative charge here, so we will get an intermediate like this. Or second possibility is this NH2 will attack on this carbon and this bond will shift here. So we will get a negative charge at para position. NH2 group attached at meta position. So in this case, this negative charge is far from this negative charge. Okay, same charge will repel each other. So in this case, they are far from each other, while in this case, they are a little bit closer as compared to this one. So this will give me major product, right? So this is all about aromatic nucleophilic substitution reaction and conjugate addition of alpha beta unsaturated compound. I hope this video is helpful to you. Thank you so much for watching. If you like my videos, please share my videos with your friends. Keep watching. Thank you.